So let's start this next section, 5.5, 5.6 we're going to do together. And then in our next class, we're going to do 5.7, 5.8 together. And then after that, we're going to do a lab, and then we're going to have a test. So just give you a schedule, so you guys can know what your schedule is going to look like for next week. So next week, again, we're going to finish up 5.7 and 5.8 on Tuesday. On Thursday, we're going to do some form of a lab, which I haven't figured out yet. I'm trying to figure out how to use Newton's law of gravity in the lab, because it's kind of hard to see. And then the following week, when you guys come back, it'll be on Monday, when your test is going to be. Okay, so keep that in mind. You got the weekend to study. I used to love tests on Monday because, honestly, you had more than enough time to study over the weekend. It's not after the Super Bowl like some other classes have tests. So I'll pride myself this year. I timed it well. Last year, I gave a big test the day after the Super Bowl, and everybody hated me. So I felt bad, honestly, because I get it. I like to enjoy the Super Bowl also. I know. He goes, there's nothing I can do. He was talking to me about it the other day. He's like, I happened this year. I'm giving him a test after the Super Bowl. It happened to me last year. It's just timing. That's all it is. It's not like anyone's doing it on purpose. But this year it worked out well for us here. All right. So section 5.5 and 5.6 together talk about Newton's law of gravity. And we've already actually talked about this before. Whether you realize it or not, when we started talking about Newton's third law for every action there's an equal and opposite reaction, we used the example of you jumping on the earth, right? And what did we say? When you jump on the earth and the earth pulls you down with a certain amount of force, what do you do to the earth? You pull it back up with that same amount of force. But the earth doesn't move. We all kept saying this. Like, the earth doesn't move when you jump, you move. It's because the earth is so massive. The earth is so massive that it has such a large value of m that the a value, ma, right? F equals ma. The a value of the earth, when you jump and exert a force on the earth, pulling the earth up, it's not really moving up. The a value is practically 0. Okay? And it really is 0, actually. So the key, though, to recognize from that problem is this. Every object near another object will influence it using gravity. So this eraser right here, these two erasers sitting next to each other, whether you realize it or not, they're getting pulled together. But the pull on them that's pulling them together from gravity, it's insignificant. It's definitely not enough to overcome the friction here. Even if it were sitting there and hanging freely, it still wouldn't be enough. You would have to take like a neutron star, something that's so dense because it's all this matter that's collapsed on itself. If that was near another one, then they would pull each other together. But we're talking about erasers here. These have pretty much no mass to them compared to what we're talking about, like something like the Earth or a star or a moon or some celestial body. So you don't really see it. But again, everything that has mass has a gravitational pull. How many of you have seen Family Guy at some point? The show Family Guy? Okay. You know Peter? Do you all know the episode where Peter starts gaining a little bit of weight during the episode? He gains weight, and Brian eventually says to him, Peter, what are you doing, man? Like, you keep eating, you're unhealthy, you're not exercising, going over all this stuff with Peter. And Peter's like sitting on the couch, and he says to Brian, like, Brian, be quiet, you don't know what we're talking about. And Brian says, Peter, I do, watch this. And he picks up an object and throws it at Peter. Anybody remember this episode? What happens? Can you guess what happens? As a result? What happened?
It gets sucked in.
Yeah, it's the objects start orbiting around Peter. And it's a joke, obviously, that Peter is so massive he's created his own gravitational field, which is what's around the Earth. It's also around the moon. Around the moon, there's a gravitational field. So there are some objects that are orbiting the moon, and those are called satellites. We're going to talk about satellites in 5.7 and 5.8, but the moon is like a satellite of the Earth. So anything that's revolving around something due to its gravitational pull is known as a satellite. So moons are really satellites. We think of satellites as man-made satellites, the ones that we put up in space to help us to send a cell phone signal somewhere. But satellites are any object orbiting another object based on gravity. So in that episode, Peter develops his own FG value. So let's talk about this specifically, what makes it up. So on the second slide, we can see what's happening here. And we can see clearly, God bless you, that the gravitational pull between any two objects is a function of their masses. And R. And in this case, R is not a radius. It wouldn't be logical for R to be a radius because how many masses do we have? So which radius would it be, right? Use logic, please. I can't tell you how many times in the past students don't know this formula well, and then they think R is the radius in the test. They put the radius in there. It can't be a radius. It's not logical. We've got two different objects. We've got maybe this object and this object. So there's no way r could be the radius because they have different radii, and clearly they're not even circular, right? So r in this problem is the distance from center to center. The distance from center to center. And you could say the distance between their centers of mass. For any spherical object, we assume the center of mass is the center of that sphere. So the Earth's center of mass is literally the core at the very center of the Earth. For these objects, it's a little bit tougher, but we're going to talk about center of mass later in the year, and you'll learn more about that concept. For this, because it's relatively isotropic, it's about the same throughout, it doesn't change much besides this layer of felt on the bottom. The center of mass is probably smack in the middle of this rectangle here, and smack in the middle of this rectangle here, inside of the object. Okay, the center of mass is inside of this object. We can't really see it. Okay, if you want to see it for an open object that's more clear, for this container, the center of mass, left the mouse on, the center of mass for this, another one, oh my god, the center of mass for this object, this is killing me, is pretty much right in the middle there where I'm pointing to. Okay, because it's relatively equally distributed on mass. Maybe it's closer to the bottom because the mouses are filling up more of the bottom of the container than the top. But r is distance from center to center. Has anyone seen that value g before? That capital G there? At some point in physical science, did you go over capital G? Capital G is called the universal gravitational constant. Capital G is the universal gravitational constant. Let's see, who developed this? Who's the guy? Where is he? I got it written down, yeah. Henry Cavendish in 1798 actually measured capital G for the first time using a very interesting lab setup where he had a rotating rod and two masses, and there was slight deviation of those masses due to the gravitational pull between them that he was able to amplify using a system of mirrors and lasers, or mirrors and lights. He was able to see that there was a small, what's called perturbation of that mass because of the simple little pull between the two objects. You can read more about that this weekend in your section of 5.5 and 5.6. Part of your homework is to read a little bit more again. And there's a whole excerpt on it on the margin of your page. It's quite interesting, actually, what he did. But Cavendish discovered capital G in 1798, 100 years after Newton came up with his law. Newton developed this law right here, but you know what Newton said? Here's what Newton said. Newton said the following: F is proportional to the products of their masses and inversely proportional to the square of the distances between their centers. That's all Newton was able to come up with. He didn't actually develop the capital G value. He recognized, though, that as masses get larger, the gravitational pull gets stronger. And it turns out it's a product of their masses, not a sum. And then he also recognized, as the masses get further apart, gravity got weaker, but a lot weaker. Not just indirectly related to the r, but r squared. So if I were to triple the distance between objects, r would increase by a factor of 9, because it's r squared. If I were to quadruple r, this would go up, or the denominator would increase by a factor of 16, because it's squared. So the relationship that exists between the distance is to the square of the distance between them.
What is that little sign?
Proportional to. Yep. And if you remember from algebra freshman year, we talked about direct and indirect variation, and usually we used y equals kx, or y equals k over x. K was your proportionality constant. In this case, it's capital G. Capital G is the proportionality constant. So again, Newton didn't really get the number, but he got the idea down. And this was his idea right here written. Okay, and then again, Cavendish came on later and figured out what capital G was to understand the force of gravity between objects. Let's see. Okay, let's keep going. Let's go to an example actually first. Let's jump right into an example. So we have two dump trucks. Equal mass experience a gravitational force between them. A very small gravitational force. Look at that number. 0.00004 newtons. A really small value of attraction. But these are dump trucks. And dump trucks are pretty massive, right? Compared to like a human body or an object, dump trucks are very massive. So we know that there's a force of attraction between them, even though it's very, very small. If they're 5 meters apart from center to center, determine their masses. So start this problem, take an approach. How would you do it? Check with the person next to you. List your givens. Think about, we only have one formula so far, so it shouldn't be very difficult to choose what formula you're using for this problem. There is a key to solve it though, so ask your neighbor if you're having trouble, talk to your neighbor about it and see what you get.
No, but it's M1, M2, and they're equal no, because it's equal mass. So you can just call it 2M.
I just didn't open the windows. I know.
Why do you really hot?
So we're going to be using two forms of fossil fuel energy to waste, and we have nothing that's going as a result.
Oh, wait, no, but we have another. Like, is it just FG to FG?
Remember, that's only the
Oh, so it's just FG.
We're trying to figure out what M is in this problem.
Isn't that what G is?
Hey, be careful, guys. You're not replacing FG with MG. That's only MG for the Earth.
Oh, yeah.
Good job, Jackie.
What do you write?
I think I got it.
R squared over 2.
I'll give some hints on the board if it helps. I'll put some hints up.
I came up with FP times R squared times
Masses will be large because they're dump trucks, but probably not like astronomically large.
R squared be on top of FG. G will be divided by the product.
Yeah, I got this. I got something different.
What do you got?
So now to bring it back.
I think I calculated it.
Square root.
Yeah, in order to get rid of G on this side.
Solve for. What are you solving for? M?
Yeah.
Because it's M times M, isn't it? Which makes
Oh,
it
I
M.
did too. I did too.
That's why I said be careful when I walk past you. That's the common mistake.
It's not.
What's M times M? It's not 2M. It's M squared. M plus M would be 2M.
Yeah.
George, that's how the same as this
Oh,
problem.
I thought you meant that MG.
That also was the last one.
I need to recalculate.
Both masses are the same.
I still got a small number.
So you won't want M times M, you just get M
FP
squared.
is,
So you're going to have to solve it.
I still got a small. I think I did this wrong. So you do R squared times divide these. I came up with a really small number.
So,
Okay, I got it. You get 3/8.
Okay, there's a small number.
Wait, let me try, guys. I'll try.
check this out.
I think we did it wrong. So one.
You can't just cancel the M's. There's no MG. Remember how FG was MG on the Earth?
We're doing this wrong.
What's pulling on this out? Yourself. That's not the Earth. We're not using MG in this problem. Now we're using this FG to get the problem. This right here is given right up there. See that? Big G is on the previous slide.
3.8.
Well, that's
Why is it so small? It's always the same.
so it's a constant. Remember I said there's called the universal gravitation constant.
Yeah, we did something wrong.
But it's easy to remember because it's 667, 10 to the negative 11. It rhymes. That's how I always remember it. You don't have to memorize capital G, it'll be given, okay? But it's kind of rhyming, 667, 10 to the negative 11. When I was in high school, it was just an easy way to remember the number. 667, 10 to the negative 11. All right, something to point out. Let's bring it back together. Something to point out here. First, listen. Several groups, and I did this on purpose today. I made sure I gave you time to work on this because there are two common mistakes. One, discuss the first one.
Replacing FG with MG.
Yeah, this is no longer mg. Because if you replace Fg with mg, you're looking at the gravitational force due to the Earth. Remember, little g is the gravitational acceleration constant on Earth. So when you use mg to replace Fg, you're assuming that you're looking at the force on the object due to the Earth. But this is not that. This is the force due to each other. This is the mutual attraction between them. So this is not accounting for the Earth. Second common mistake, and a couple other groups made it. Anybody remember what the other one was? Yeah.
Since M and M are the same mass, you can't combine them to make 2M because they're being multiplied, so they'd be n squared.
Yeah, this becomes m squared right here. And a lot of groups made this 2m. When you see m, don't think 2m. It's not doubling m, it's squaring it. So it becomes the following. Okay, this is what it becomes right here. And then it's just a plug and chug. Everything is known. Okay, capital G is given. That's never going to change because it's a universal gravitational constant throughout the entire universe. If you want to write that down next to G on the previous slide, you can. It never changes. If you're on Jupiter, if you're on Mars, if you're in the middle of empty space, if you're near the center of the sun, G is still 667, 10 to the negative 11. R is given as 5. Fg is given as 4 times 10 to the negative 5 newtons. Solve for m. What do you get for m when you solve for m in this problem? What do you get then?
I got 3,872.2.
I'll leave it like that then for now, if it's 0.02. That sounds right. 3872. 3872, yep. Okay, check your work, please, if you need to. Go ahead and multiply by r squared, divide by capital G, and then square root your answer to get m by itself. Okay, again, multiply by r squared, which makes it Fg times r squared, divided by capital G. That'll give you m squared, but you want m, so go ahead and take the square root. Little g is the gravitational acceleration. I'm trying to say little g, but to laugh at that. It's the gravitational acceleration only on Earth. Only on Earth. We're going to prove, or we're going to demonstrate the value of little g using this formula in a little while. Okay, but if I go to the moon suddenly, we've talked about this already, right, with projectile motion. Anybody remember on the moon? Anyone remember on the moon? Gravity on the moon is approximately, anybody remember the number? Nice, good memory. 1/6 of the Earth. It's about 1/6 of the Earth. So when you want to think about the gravitational constant on the moon, or the acceleration, it's 9.8 divided by 6. That's what it is on the moon. So what do we say? Remember I joked, you feel like you weigh 6 times less, you want to lose weight, go to the moon. Good luck. No, you can't breathe on the moon, so really good luck. All right, let's look at the next example here. What is the force of gravity acting on a 1,500 kilogram spacecraft when it orbits 2 Earth radii above the Earth's surface? So I also give you values of the Earth's radius and the Earth's mass. Those values we'll talk about where they came from too. But for the sake of this problem, here's my first recommendation. Draw yourself a diagram. And if you don't know how to draw a satellite, you know how you draw a satellite? It's really as a spacecraft. A satellite is a bow tie. The easy way to draw a satellite is a circle with 2 pieces coming out at the side, like a bow tie would look. Okay, when you're drawing on your diagram. You don't have to make it a bow tie here. Okay, but please draw yourself a diagram. That's an ugly looking Earth, but that's my Earth. Let me just make it better. Hold on. All right, there's the Earth. and the satellite is 2 Earth radii above. So this is an Earth radius right here. That's RE, the Earth's radius. So it's 2 Earth radii above the surface. Everybody with me? 2 Earth radii above the surface. So it means that it's an additional Earth radii and another additional Earth radii before we get to the satellite. Everybody see what I'm doing? I'm purposely drawing all these segments to demonstrate to you how we would visualize this. So how far is the satellite from the center of the Earth? Because remember, it's center to center. R is equal to the distance from center to center in all of these problems. What is it, Mauro? It's 3 Earth radii. So in this problem, it's good to recognize right away that the R value is triple the Earth's radius. And we're given that value. It's in kilometers. We'll convert that. That's fine. Okay, but this is really important that we see. It's 2 Earth radii above the surface plus the Earth's radius itself to get to the center of the Earth. So it's really 3 Earth radii from center to center. Do I care about the size of that satellite? Why not, Jack? You're like, no, definitely not. You're right, but why not?
The masses cancel out.
Good stat, though, Jack. But you don't care about the size of the satellite. Why?
It's just so small. It doesn't matter.
So, as a result, because I'm going to use the mass of the satellite it was given, so I'm not going to drop that off. I'm saying the size, I said, the size of the satellite. I didn't say the mass of it. Why don't I care about the physical size of the satellite?
Compared to the radius of the Earth, it's like negligible.
Compared to the, God bless you, compared to the radius of the Earth, it's practically negligible. If there's a radius of the satellite, maybe it's like what, 20 meters? Compared to 6,380 kilometers, that extra little radius is going to be insignificant. It's not going to matter. So although I might think of it like, oh, Mr. Howell, look, if I zoom in far enough, I haven't really made it to the center of the satellite. I have to account for this little radius right here, right, this distance that I continue. And assume this went all the way there, okay? Assume that I drew that arrow all the way up to it. I have to account for that little red vector there because it's a little extra length, but it's really not significant. It is what we call negligible. Okay, negligible. So as a result, let's take a look what we've got. We've got the radius, or the distance from center to center as triple Earth's radius. We've got the mass of the Earth is given. So let's go right to our formula. Capital G, M1, M2 over R squared. Capital G, 6.67 times 10 to the negative 11. The units of that, although seemingly difficult, are not that hard to memorize, actually. And let me show you what I mean. If you have trouble remembering the units, it's on your formula sheet, obviously. But if I think about it, I want to get Newton as my answer. So there's newtons in there. I want to cancel R squared in the bottom, so there's R meter squared up top. And I want to cancel kilograms squared up top. So the units of this come about from the formula, right? Look, this is kilogram times kilogram. That'll cancel with kilogram squared. This is really meter times meter. That'll cancel with meter squared. So what am I left with? Which is the value of a unit for force. Julia.
Wait, where'd the N come from?
Where'd the what come from?
The N.
Newton? Those are the units, just the units.
Oh, so there's no number.
Well, I'm not done with the formula yet, so that's what we're going to have for these two. And then we're going to have this guy squared. So this is just G right here, Julia. I'm putting it in the numerator, sorry. Sorry, guys. I put this in the numerator versus in front. We should recognize, I know I'm not saying to you, but in general, these are the same ways. Okay, I have a tendency to put it in front of here to show that it's like a proportionality constant. But if you put G in the numerator, it's the same thing, and then you have your two masses here still. Again, the mass of the Earth, 5.98 times 10 to the 24 kilograms. The mass of the space shuttle or satellite, whatever we're talking about, 1,500 kilograms. And then the distance between them is triple the Earth's radius, but that's in kilometers. It's in kilometers. So I got to write up here that the Earth's radius is 6,380, but then if I'm putting it to meters, I got to add 3 zeros to the end of it. And that's the Earth's radius in meters. Okay, that's the Earth's radius in meters because it was given in kilometers. Remember, the only unit that we don't care about breaking down to its base unit is kilogram. Kilogram is actually the base unit for mass here. Okay, it is the unit that we use for mass. So it's triple that number. Okay? So it's a bit of a work on my calculator. If you don't know how to use your calculator, you will run into problems here. How do we use scientific notation on a calculator that makes it a lot easier? And don't answer with multiplying by 10 times 10 to the 24. What do we do on the calculator? What button is it? Yeah, there's a capital E button. And to do that, the command is located right above the number 7. It's the key above the number 7, and you have to press second to get to it. You see capital E right there? That capital E will put a capital E on your screen, and it will look like this. Here's what your calculator screen will look like. 6.67, capital E. That's what you're seeing right now, right? This, take a look please, this symbol on a calculator means times 10 to the, without the exponent. It takes the place of the times 10 right here. So we have to put a negative 11 after that. That is how I write 6.67 times 10 to the negative 11. Again, it's important that we know this, because your answer you're going to get sometimes will be astronomically large or really, really small. And the calculator is going to give the answer with this notation. Okay, it is not going to look like this at all on the calculator. So recognize that times 10 to the is replaced with this capital E. Then that gets multiplied by the Earth's mass, 5.98, capital E, 24. And then that gets multiplied by 1,500. And then that's all divided by triple this number, squared. Okay, that's what your entry on your calculator is going to really look like. I recommend that you do the whole numerator first, okay, just to be safe. If you're nervous about, did I put enough parentheses, did I do this right, just do the numerator out first, then divide by the denominator. Okay, then divide by the denominator. Triple this number, squared. If there's an issue on this problem on most tests, honestly, it comes from the calculation. It doesn't come from the math itself. Okay, it comes from the calculation. And you know when that happens? That happens when students don't practice. When they don't practice using their calculator in class and or at home with scientific notation. And I'm being honest with you, that's where it comes from. So please, when you're in class, when you're at home, practice this on your own. Don't just assume the person next to you is doing it right. So, oh, you're okay, I'm all right. My number is 1633 newtons, approximately. Approximately 1633 newtons. I know it's around here. I'm rounding it, okay? I want to make a point, though. I want to talk about something now. This object, this space shuttle, satellite, whatever you want to call it, is not at the Earth's surface, but it's 3 times as far away. Okay? It's 3 times as far away. Tell me, please, calculate it, what would the gravitational pull on this satellite be if it was on the Earth's surface? Just on the surface. How would you do it? What have we been doing all chapter? Forget this new stuff. Forget the new stuff. What have we done all in chapter 4? How do you calculate the gravitational pull of an object on the Earth's surface? What formula? Fg equals mg. So go ahead real quick and calculate 1,500, the mass of the satellite, times g, 9.8. Go back to old school methods. Forget this formula for a minute again. Go back to chapter 4 and calculate the weight of this object using mg, please. Calculate the weight of the object using mg. You're going to have a number on your screen. You have a number on your screen. Now, if the object is 3 times as far as it normally is, what factor does gravity go down by? Think about the formula here. If it's 3 times as far, what factor does gravity go down by? 9. Because if I triple this, it's squared, isn't it? So take your answer you just got and divide it by 9. Pretty sweet, right? Okay, proving, again, that Fg equals mg is valid on the surface of the Earth. But if I'm twice as far from the surface, I can divide by 4. If I'm 3 times as far, I divide by 9. If I'm 4 times as far, I divide by 16. So if you know how far away something is as a multiple of the normal distance, right? This is the normal distance between an object and the center of the Earth. If you know how far away it is as a multiple, you can simply just do mg and divide by that multiple squared. Or you can use your formula here to get the same answer. Now, it's not as easy as it sounds if I suddenly say something like, An object is 2,000 meters above the Earth's surface. Now you don't know what that multiple is, so you got to say, all right, well, I'll take an Earth radius and I'll add 2,000 meters to it, and that's how far they're away. So it's not always going to work that you can just divide by a multiple of something. It's because we are currently triple what we normally are that it worked to divide by 9. Okay? All right, let's go on. So let's talk about this value little g. Okay? And this is little g for any planet, not just for Earth. We'll talk about Earth specifically, but this is for any planet. So earlier, a couple of you guys right away replaced FG with MG. And I said you can't do that because we're looking at two dump trucks pulling each other toward each other, not the Earth and the dump truck. But what if I was talking about this keyboard right here and the center of the Earth? Well, if I'm looking at an object on the surface and the center of the Earth, and I'm finding the gravitational pull between them, that's just your weight. Remember, your weight is the Earth pulling you down. So if I were to think about this and I say, well, you know what? This is the formula we just wrote a little while ago. Right? That was the formula we wrote. But then I say to you, well, now I'm telling you that you're on the Earth's surface. So you could also tell me that this is another formula that's acceptable to calculate weight. Those formulas are the same when you're on the surface of the Earth and you're looking at the weight or the gravitational pull between the Earth and that object. So if these are the same values, Fg, we can set those equations equal. Thank you. So we get mg equals g m1 m2 over r squared. But here's the thing. It looks like m1, m2, and m are all different. But really, what is this m? What is this m? Is this the mass of the Earth or the mass of the object on the Earth? Which one of those two is it?
The object.
The object on the Earth, right? And if I'm looking at these two m's, one of these is the Earth and one of these is the object. Because we're looking at the gravitational pull between the Earth and a random object on the surface. So one of these m's over here is the same as this m over here. Because again, one is the Earth and one is the object. So if I'm looking at any planet, here's what I do. I make a generalization. I say the following. mg equals gm capital M over r squared. And what do you think capital M is? Capital M is the planet's mass. And little m is the object. If you want to use MP and MO, that's fine. For massive object and massive planet, that's fine. But it's good to recognize that one of these is the planet, one of these is the object. Now you can cancel the objects that are on both sides. This m is the same as this m right here. And what are we left with? Oh, there it is, little g. Little g is big G times the mass of the planet it's on, divided by the distance from that object to the center of the planet. So what would we call that? The radius of the planet, really. Visualize this if you can, please. Visualize this. Here's your planet right there, and there's your person. So how far apart are they? Well, it's just whatever the radius of the planet is. So that r in the denominator is simply the radius of the planet. So if I want to find out the gravitational constant on Jupiter, what do I need? I need the mass of Jupiter and the radius of Jupiter. This is given. It's a constant no matter where I am. If I want to find the gravitational pull on the moon, which is, we said, 1/6 of the Earth, the mass of the moon goes here, the radius of the moon goes here. So no matter what planet you're on, this is my overarching formula to find the gravitational constant. You could also find it by doing a free fall. You could also find it with the picket fence we did. God bless you. You could also find it with an inclined plane ramp. Later, when we look at a pendulum swinging back and forth, you can find it with that. Little g can be calculated so many different ways. This is just one of the verifications that we can use to say, oh, it's around 9.8. It's around 9.8. And go ahead and do it. Right here, you know these numbers. They're given for the Earth. I gave it to you in the last problem. This is 667, 10 to the negative 11. The mass of the Earth was like 5. What was it? It was on the previous slide. 5.2 or 5.98 times 10 to the 24th. Yep, 10 to the 24th. That's m here for the Earth. And the radius of the Earth is 6,380,000 meters. These values are in the previous problem. So again, go ahead and plug them in and prove that g, little g, is around 9.8. Okay? And that's the case for all planets. For all planets. And you'll get around 9.8. So here's the interesting part, by the way. So remember that guy I was talking about, Cavendish, Henry Cavendish? He discovered, or he was able to come up with the value of big G. But prior to this, no one knew the mass of the Earth. That was actually uncalculable at that point. There were estimations, but nobody really had a fine value for the mass of the Earth. But because they were able to do free fall experiments, G was known. So pause for a second and take a look up. This was known from experimental behavior. They were able to drop things and figure out the acceleration little g. This Cavendish discovered about 100 years after Newton came up with his law. This actually, the radius of the Earth has been known for a long time. Based on shadow angles, like ancient civilizations knew the radius of the Earth. Once they recognized it's spherical, not going to drop off, that the Earth is flat thing. So these were all known at this point in time. Once Cavendish discovered capital G, that's when the mass of the Earth was actually calculated. So the mass of the Earth was unknown for the longest time. Cavendish's experiment is what allowed us to figure out what is the mass of the Earth. Okay, really interesting stuff that you wouldn't really recognize right away, but experiments are what lead to these answers. Okay, proving again that little g is a constant on the Earth. Now we're going to see in about 2 seconds or so that if we move up on the Earth, it changes slightly. And we've talked about that already. What stadium did I talk about? Yeah, either the Broncos or Coors Field, either one. Mainly Coors Field feels it more because baseballs are different than footballs, and we'll get into that. But yeah, in Denver, where it's called literally Mile High Stadium, because it's a mile above sea level. So it's further from the center of the Earth. So R is increasing, isn't it? If R is increasing, then this overall value is going to decrease, which is why gravity at Mile High Stadium is slightly lower. Let's prove that. Okay, let's take a look at the next. Oops, example and prove that. So Mile High Stadium in Denver, Colorado is literally 1 mile above sea level, 1,610 meters. The nearby baseball stadium, Coors Field, is slightly lower at an elevation of 1,580. Determine the gravitational acceleration that baseballs feel at Coors Field. Ignore this, that was last slide. Okay, at Coors Field, ignore this little symbol here, please. Oh, there we go. So let's take a look. We want to know the gravitational constant. We could say here, we could start with this formula, but you know what? Based on what we wrote on the last slide, let's jump right to that next slide, right? Or that last formula. On the last slide, we wrote this. We said G equals capital G, mass of the planet over R squared. This is what we came up with, right? But suddenly R is getting a little bit larger because we're not at an Earth radius from the center, right? When we're in Denver and we're at one of these stadiums, technically you make believe I'm going to put a mountain, okay? This is us right here. You climbed a mountain. If you go to Kilimanjaro, actually, it's even further. Or Mount Everest is further up. So really, the distance is the Earth's radius plus this extra mile right here. I'm going to call that D. Again, the distance between you and the center of the Earth is the Earth's radius plus that extra mile. There's an extra mile there. So when we calculate R, we're going to have capital G, mass of the Earth, over the radius of the Earth plus that extra distance D. And that extra distance D is given as 1,580 meters. So again, calculating little g on any planet, the assumption is that we're on the surface of that planet. But when we're at Mile High Stadium, we're a mile above the surface. So we have to add in the value D, which is 1,580 meters, about a mile. About 1 mile. That's what this value D right here is. Plug and chug at this point. 667, 10 to the negative 11, times Earth's mass. You do not have to memorize that either. The Earth's mass and radius will be given. It is not something you have to memorize. 598, 10 to the 24. All over. The radius of the Earth, again, you don't, oops, I put that comma in the wrong spot. You don't have to memorize this. Plus the extra mile, or approximately the extra mile. What do you think? Before you calculate it, a lot of you are going to go right to the calculator, which is good. Before you get to the answer, though, what do you think? how much is this number going to affect this number? Is it going to be very significant? Little? Not at all? What do you think? What do you think? Yeah.
Well, I mean, it's being squared also, so it is going to make a decent impact.
The square definitely has an impact, but this is also being squared, right, technically? The sum is really squared. You're not squaring them separately. We know that.
It's probably gonna be like 9.812 or something.
Uh,
Oh, sorry, just like 9.79.
yeah, something slightly less. Slightly less. Let's figure out what it is. Sorry, I paused you there. Go ahead and calculate. Go ahead and calculate. Let's get that gravitational pull or acceleration, the gravitational acceleration on. And give me 2 decimals for this, please. Give me 2 decimals. We know it's 9 point something already.
79.
What do you got?
9.79.
7.9. Agree with Nick? Agree with Nick, yeah? This is actually really insignificant, it turns out. So it's not really the gravitational constant that affects baseballs at Coors Field. It turns out that the air is actually much drier the further you go up, which is why mountain climbers sometimes will bring oxygen tanks, because the air gets real thin as you go further up a mountain. So it turns out that the dryness of the air dries out the baseballs. It makes them harder. The harder the baseball, the more pop they get off the bat, the more of a elasticity. Have you ever dropped a Super Ball? You know what a Super Ball is? Those bouncy balls? You drop them and they almost get back up to the height, right? They have a very high what's called coefficient of restitution. It's how much it's bouncy, how springy it is. A tennis ball, though, a tennis ball will fly very easily, but if you drop it, it's not going to bounce nearly as high as a Super Ball will. A ping pong ball will barely bounce high. We're going to do this actually when we get to kinetic energy, potential energy, to talk about the coefficient of restitution. But a baseball, when dried out, suddenly becomes very bouncy. That's what actually gives the baseball the extra boost. Now, footballs similarly behave differently at the elevation, but not as much as a baseball, because a football is pumped with air. You're not drying it out anymore. It's not drying out the football. The inside is air still. Okay, now, does the air pressure go down? It does slightly. So the ball gets a little bit deflated. There are New England fans in the room. Gets deflated a little bit. But what they do is they pump up the ball to make sure that it's the right amount of pressure. What do you think they do with baseballs? What do you think they do with baseballs in Denver? They do it. What do? They don't put it in water. They juice it, yeah. They put it in a what? What do you think? To keep it moist. Louder. Humidifier. It's called the humidor. But they put it in a container. It's no joke. You ask anyone, go to Coors Field, the game balls are kept in a humidifier. And as they're actually being used in the game, they get taken out and tossed out there. Because the ball gets so dry compared to its counterpart, a humid ball. Okay? We have one more example. We're not going to have time, which is fine for today. But listen, over the weekend, you have to finish your lab, which most of you finished already, and a lot of you turned in. If you're done with it, you can turn it in today. You also have to read 5.6 and 5.7. I did not assign the homework yet, but if you want to, you can get a